Hey, hi everyone, this is Vivek, and today we're going to talk about this problem called Construct Highways from Atcoder Beginner Contest 239. And this particular question is on graphs, and we have given some conditions and we have to create a graph, okay, construct a graph. So let's go into this particular problem. Also, this is more of a constructive kind of a problem, so we will try to see how to approach constructive graph problems in general. And if you learn a lot of different things from this particular problem, whatever is your observation things or your learnings that you would like to generalize to other problems, please make sure that you comment them down below. Number one, it is definitely going to help me out to kind of promote these videos to more audience so that more people kind of find out the content like this. Also, the main reason why I always ask for comments in general is because these are going to work like encoding for you, and you're going to remember whatever you write for a very long time. So it's like a independent practice for yourself. Okay. Also, the third reason is you'd get others comments to kind of go through what they have learned and then finally write your own comment, right? So that's something that we follow in every particular video of this particular series. Again, let's come back to the problem and now start learning, right? So construct highways. We have this particular setup where we have n towns and m highways are already constructed. And now we need to construct n minus m minus 1 number of highways such that like the degree of each particular node is given to be di, like it has to be made di, right? And like they are all bidirectional kind of thing. After adding all the edges, the second condition is the whole graph should be connected, wherein we can travel from one pair between any pair of nodes using some number of highways, right? So these are the two conditions. So you have to create a connected graph, and you have to add these many number of edges, and every node should have a degree of di, right? That's the setup. How do we build such a thing? Now note that it's given in the problem that determine if such a way of construction exists. If it exists, print 1. Okay, so that is important. And the number of nodes is 2 to the power 5, so it's a very general constraint. So before we start with this kind of a problem, you first have to note that you are asked print 1, right? So whenever you are asked print 1 problem, right, in these kind of construction setups, in general it's more of a constructive problem, or you will have to devise some sort of procedure that is going to kind of check that whether it's working or not. And the second thing is, if it is working, then at the end you should be able to generate the whole solution. So it is more of like finding a procedure rather than finding just a number, right? So this is how these kind of things helps us in solving problems, that if you have been asked to print something, most probably there is some procedure that it needs to follow, right? Also, these constraints are given pretty large, so it has to be something very generic. And the next thing that you have to observe for this problem is that the total number of edges initially were given m. So there are m bidirectional edges that is already there in the graph. And then finally you add n minus m minus 1 edges. So the final total number of edges that is going to be there is n minus 1 edges, right? If you add these two. And there are n nodes. And finally it has to be all connected. So n minus 1 edges, all connected graph, n nodes. That's only possible if it's a tree, right? So the final graph that we are building is a tree, and we need to make sure that everything is connected all together after adding these extra edges, right? Now let's have a look at how do we approach this kind of a thing. So we have read the problem, this general procedure flow. If you don't know what flow we follow, like I have talked about this particular 5 phases, check that video out. It's going to be there in the I button. But we will follow the read and then we will observe few things. We have made already an observation and solve the problem more or less. And then the third one is going to be to formulate and how we're going to code this up, right? So let's try and see some examples, and that's going to make much more sense. So finally we know that, let's say there are these 5 nodes, right? After adding all the things, it has to be a tree. So how do we check that whether it's going to be a possible, whether there's going to be a possible solution or not? A very simple way would be to maybe check the degrees of each node, and the sum of those degrees should be equal to 2n minus 2, right? We know that the sum of degrees of all the nodes of the graphs has to be equal to the 2 into number of edges. This is always true in any particular graph, right? Because every edge adds degree to 2 nodes. So every edge has 2 contribution, and if you sum that across all the nodes, this has to be 2e. So in this case there are n minus 1 edges, so in total this has to be there. This is certainly, this has to hold certainly. Next is there are some number of edges given initially. If already, like let's say you are given some d1, d2, d3, d4, d5, right? If by the initial edges itself, if some particular node has a higher like degree than the desired degree, then you cannot really remove edges, right? You can only add more, so you can never create that, right? So these are some things that you can check easily, but again, we are not over here to kind of like manually find out each case, right? It's better to find out some procedure that will solve this problem, and that essentially, like if you cannot do that procedure, then it will tell you that you cannot really get the solution. So this is something that we generally use in most ad hoc or constructive problems. So how can we do that? So the number one thing is the final thing is going to be a tree, right? So let's think about it this way, that maybe this edge is there, but it's not present in the initial one. And let's say this edge is not present in the initial one. So the initial graph looks something like this, right? And then it's given that there has to be 3 degree of this. So right now it's 1, there has to be 3 degree of this. It is given that the degree of this has to be 2, this has to be 1, this has to be 1, this has to be 1. So it's given like this, right? So from this itself we can infer that you have zero potential to this, which means you can connect only 0 nodes to this. You can connect 2 more nodes to this, you can connect 1 more node to this, you can connect 1 more node to this, right? So this is something that you get as an extra information. Why? Because as soon as you get this, you know the final things, you know the current degree of the node from the initial m edges. So you know how much more edges can you add to each node, right? Now there is this property that after adding those n minus m minus 1 edges, it has to be all connected, right? So you will, for every edge that you add in the tree, in the graph, it has to connect two different components, or else it's never possible. Why is this true? Because at the end there is going to be n minus 1 edges and everything is connected, which means if you remove any number of edges in a tree, this is a property of a tree, that if you remove any particular edge, you always create two new components. Okay, remove any edge of the tree, you will create two components. Again, remove any other edge, you will create two components. So for every edge that you add, you have to merge two different components for sure. Okay, so this is something that is true for this particular problem. This has to be true. If it is not true, then there is some problem. Okay, when I say some problem, which means the graph is it's not feasible to build the solution. Okay, so you have two potential to this, you have one potential to this, you have one potential to this. Now this is the essential nodes, so these are the essential nodes and they have these particular things with it. So finally you see that okay, you can connect this with this with this, and then they kind of satisfies these three requirements, and then you are done with the problem, right? So that's how like we are trying to do. But how do we actually do this properly? So we make some observations finally that we're going to use going forward. So over here you can see that there were these bunch of one extra edge requirement nodes, right? One extra edge required and so on. So there are going to be bunch of such nodes which require only one extra edge. So right. So let's say I'm just going to build a bigger graph this time. Okay. And let's add some thresholds to those things. So when I'm writing something in blue, which means this is the extra number of nodes you have, right? So you can always subtract the current number of nodes and the given number of nodes to get the extra number of nodes, you can extra number of edges that you can add to the nodes. So let's say you can add 2 more to this, 1 more to this, 1 more to this, right? 3 more to this, or 4 more to this, and then 1 more to this node. Okay, this is something you can, like, let's say keep. So how can we keep doing the procedure for this particular thing? Maybe these one nodes that we have, like the nodes that have exactly one requirement, these are something that are important. Why? Because think about it this way, that whenever you connect this particular node with some particular node, right, like this, So this node now kind of gets merged with this component, and now you have a 3 requirement kind of a node over here. If you connect this with this, it will become 2 requirement kind of a node. If you connect this with this, it will become 1 requirement kind of a node. And then if you connect this with this, it will become 1 requirement kind of node. And it is not satisfied. So this is not a suitable graph, right? Let's say there was this one more edge, one more node with a 1 requirement, then you could have got connected it with this. But anyways, let's see this particular graph back. Right, and just to make it like a proper one, I'm just gonna add one more over here, just so that one component has 2 nodes which have requirements. Right, let's see if we can connect them. So what we now find for this particular problem is these components which has exactly one edge, one node with one extra. Okay, why? Because once you have a component, right, either it's like an internal node or an like a leaf node, right? So think about this particular portion that we're gonna build using the rest of the nodes, right? It's either going to be exposed with just one edge, or it's going to be like an internal node which is going to be connected to multiple number of edges, right? It has to, since it is a tree, there has to be some parts which gets exposed at the end, right? So the one node has to be an exposed portion to it. So this has to have some outgoing thing, and it has to end somewhere, right? So let's kind of club all of these port nodes. Let's call these nodes as one. Like let's call this something like anything. The components with one number of node, and let's call some other node, the rest of the nodes, rest of the components, right? These components. Let's say this component, this component, this component. Let's call this C greater than 1. Or let's call this C2. Okay. So these are the component 2 nodes. Now what we do is, as long as we have some particular node, some particular component to node, what we will do is we will take that node, okay, and we will find components with just one exposed node and keep connecting them. So we will find any one of them, let's say 4, and we will find the components with just one, and then we will try connecting them. Let's say it can be any node, any particular component with more than one exposed node. Now, why exactly are we doing this? Why exactly did we came to this particular observation? Because there is this distinction between the ones and the things. So it's like there is this component which has 2 exposed part, there is this 2, there is this 1, 1, 4, right? And you have to kind of connect them. So it's best to kind of merge this one with the largest one, or maybe one with any one of the other things, as long as that doesn't become 1. So if you merge this 1 with this 2, suddenly this 2 becomes 1 and this becomes 0, right? Because when you make an edge, that makes a connection between the two, and those two exposed port not really exposed nodes kind of vanish off, and then it just leaves off one more. So what we can do is we can connect this with this, right, and it will expose this to this, right? And then we can connect this and this. If you connect these two, then obviously it will be left with one component with 4 nodes, and you cannot really connect intra node. So note that if you add an edge inside a component itself, let's say this between these two, even though the exposed nodes do decrease, but it's not forming up a final tree, because remember the observation that we have enough edge only to connect all the nodes, right? So we have only sufficient amount of edges to connect all the components. So every edge that we add has to be between two different components. You have no room for adding edges that are gonna keep it in the same component. So that's what makes this problem a bit solvable, because or else it would have been fairly difficult. But in this case, every edge has to be between two different components, and when we have to merge, it's always best to keep our room for more number of components with just a single exposed node. Why is that so? Because they are like something that can plug to any node, right? If you have some particular node, some particular component which has more exposed node, you cannot really connect them together, right? So the more nodes that you have which are of size 1, it's better. So the way we will do this is, let's say you have this component with 2, 1, 1, and then I'm just gonna add like, forget this 1 over here, let's add one more 1 and then a 4, right? And then we will add one more node which is of 1 extra demand 1. So this is called demand, which means 1, right? So let's add that as well. Let's see if we can do that. So what we can do is we will club all the nodes which are having one demand. So one over here, one over here, one over here, one over here, right? And they are kind of kept over here. And then there are a bunch of nodes which are which require more than one. So what we'll do is we will keep combining the things from the two sides and make them merged. So one merge with a node of this size 4, and it will merge these two components. This will vanish off and this will become 3. This merging this one with this 3 will make this one vanish off, this will become 2. Then if you merge this one with this 2, then this will vanish off and this will become 1, and now this is a 1. So once it becomes 1, shift it to this side, okay, because it's now equal to 1. And now you have this 2 1 that you can combine to this 2, and then you would be having 2 1s left because this 2 will become 1, and then you can just combine the last 2 1s. So that's the whole procedure that we follow. This is kind of a constructive or ad hoc-ish process, but the reasoning why we kind of do it from the first instance, like if you have to think about this on your own in a contest, the way you think about this is it's always best to retain as many number of ones as possible, and we can never connect two components which have one and one among them, right? Because if you connect two components which have just one exposed nodes and you just connect them, it is never going to get connected to something which is outside it, and that component gets closed off completely, and you can never connect it to the rest of the graph. So it's only possible just once at the end, never before that. So it's never in our interest to connect two components with one sizes each, one exposed node each, right? So that's what we refrain from, and that's why we connect nodes always from this side count, like one exposed components and greater than one exposed components, right? That's what we keep doing as long as we can do it. And the thing is, any component that has more than one exposed node, after decrementing some time, will become this one exposed node component, and we will shift it to the other side. So that's the main algorithm. So the algorithm is essentially keep connecting nodes from a component that has one exposed node and from a component which has more than one exposed node. Keep doing this, and finally you will reach to a place where you will have just two components with one exposed node each. Connect them, and if all of this worked, we have a solution, or else we don't have a solution. That's essentially the algorithm. And if you run this up at any particular place, if you fail that, if you fail or if you face that it's not being possible to add an edge, it's so you can say that okay, it's not, it's there is no solution possible, or else there is a solution possible. Why is this working is a kind of non-intuitive process. I guess this is the most ad hoc or observational part to this particular problem, that how do you come up with this. The reasoning, as I said, is mostly going to be you have to have this intuition that most probably this is the way we are going to merge this, because it's a constructive problem. And the reasoning why you can kind of prove is every edge, number one, every edge that is being used. So how are you kind of building this? You have some observation list. Every edge that we have is going to be used to merge two components, right? So no connection among the same component, number one. Number two, if you connect two components of one exposed node each, that kind of combines into one component with zero exposed nodes. Now you cannot really connect that to the rest of the graph. So you cannot connect two components in one and one. You cannot add an edge between a component which has two no exposed part among itself, because then it will not be a tree finally. So it has to be across these two boundaries. So just keep connecting them. If it's not possible, you will not be able to make it up. Okay. How to formulate this up finally? So this is a problem where formulation is a bit difficult. I mean, in general, we have solving part as difficult, but this problem, I feel formulation is a bit difficult. And how will you kind of implement this? It's not as easy as it seems, right? How do we formulate this particular thing? Formulate, right? How do we formulate this particular thing? So we have to use some sort of DSU or union find, because we need to make sure that like nodes in the same components are treated like kind of similarly. So what we will do is, like, this is just one of the ways in which you can implement them. I mean, obviously you can go into submissions and try and see if more submissions if you want to see how you can implement them. But the way I would go about implementing this is maybe like kind of building off some component list which are having just one exposed node and greater than one exposed node, these two parts. So let's say there is this graph, there is this graph, right, wherein we have one exposed node, two exposed node, and then one exposed node. So what we'll do is we will mark them with components like 1 2 3, and then I will put 1 2 and then 3 over here. And then for every component, like, these are not really the node numbers, this is going to be the union finds leader, like you have a root of the union find, right? So that's what we're going to push it in this kind of list. And then what we can do is you can kind of go through all the nodes of this C1 and for any node, maybe from the front or end, you can kind of pick this node. uh, like it has two occurrences to it, right? Its size is 2, so you know that it has two requirements. So you can pick out any one of the numbers, pick out any number and merge these two things. You can find the exposed part, keep the exposed nodes in a component saved in a separate list. You can find it out and then merge it with this particular nodes, one of the nodes, and then move, like whenever there is a final one left, just add it to this particular part. And then finally you will have these two components left, just to add an edge between the two corresponding nodes, and you will get the things. So you will have to use union find, use the leaders as the representative of the components, and then inside that component, which are the exposed node, you will have to keep a vector of list. So that's what goes into the implementation. Rest is going to be how you want to implement it up, and that's a very good exercise. So make sure that you code this up after this particular video, and you will learn a lot. Okay, so now, as we have kind of talked about how you can kind of go about solving this problem, there were very important key learnings, right? That how did we build this kind of an ad hoc thought, right? How did we build this constructive algorithm? So whatever you learn from this, make sure that you write it in the comments, and do like and subscribe to the channel, because we're going to be creating more such content. I hope you're liking the kind of content that we are building. If you have any suggestions, let me know in the comments, and we'll be working on that, right? So that's all for today. Thanks for joining in, and see you in the next episode. Bye bye.